Good morning, everyone.
Good morning.
Should we start with a few questions so that let everyone join and then we can complete metallurgy today? Let's see. Give me a minute. Answer a few questions first. Very good. Y- Everyone is attempting. Good thing. But I'll right now go to the next question. At least two questions together we should discuss. No. I'll give you options here also. Okay, question one, question two. Okay, I'm getting correct answers. Yes, very good. For the first one, the correct answer is NO2. NO2, when you add water to it, gives you a mixture of HNO3 and HNO2. So basically, your NO2 is undergoing a disproportionation where plus 4 is getting converted into plus 5 and plus 3. B is the correct answer. 1B. Any doubt, you can always ask. You can always let me know. I'm drawing H3PO4. That also two molecules. On heating, when it loses a water molecule, H4, P2, 1, 2, 3, 4, 5, 6, 7. Cancel, cancel. Why is obviously HPO3 whole twice? There's no other option. And here phosphorus is plus 5. Here it's plus 5. When it just loses water, will it become plus 3? No. Yes. Yes. No, yes means no. Whatever I said, no. Whatever I see in the chats is yes. One or two more before proceeding? Yes. Why not?
Ma'am,
You have to identify the incorrect reaction. The meaning of the first question, sure. But I'll write it here. I'll explain it in this slide after giving everyone one question. Okay. Incorrect reaction is so everyone attempt this question. Let me explain, Nandana. Yeah, if you have answered also, then wait. Nandana, the meaning of anhydride is acid minus water. So what happens here is I take H2SO4. I take out a water. Remove H2O. I'm left out with SO3. So when an anhydride, that means SO3 is the anhydride of H2SO4. SO3 is the anhydride of H2SO4. So when it's anhydride of H2SO4, the oxidation number of that element in anhydride and in the acid remains the same. Number one. Number two, it was found out that when you add water to, say, when you add water to N2O5, you get HNO3. And this is plus 5 and this is plus 5 as well. So anhydride and the acid will have the same oxidation number of the central atom. For NO2, it was found out that it disproportionates in water and produces both the acids. Many books you will find out as NO because HNO3, I'm sorry, HNO2 is highly unstable. It again decomposes giving HNO3 and NO. That's a different case. But right now, NO2 in water, when you add water to an anhydride, it should give you only one particular acid, and that also the acid and its anhydride should have the central atom in the same oxidation number. But in certain cases, but in certain cases, what is seen is like NO2. It's an acid anhydride which on addition of water produces two different acids because it undergoes disproportionation. So that's the reason it's known as mixed anhydride, which on hydrolysis gives you a mixture of two different acids. Fine? Okay? Okay, fine. Please feel free to let me know whatever your doubts are. Okay, here should I go back to the chats and check what is the answer you people have given? I'm planning for one more question. Meanwhile, class. Everyone thinks it's D? Yeah, I was searching one more question. A little bit difficult one. Everything seems too easy for you people. Yes. Is it D the correct answer? Yes. One more and then we have to complete metallurgy, no? We should not forget that. Okay. So XeF2 reacts with PF5 to give. Very good. Again, again I'm getting the correct answer here. But I would end up asking you one more question. Try to recollect what did I teach you from beginning. All possible things as much as possible. Now we have to continue our discussion also. Let us now continue with our discussion, and for that we should answer these two questions, right? Yes. So, students, here B is the correct answer. And for the fifth one, 4B many told. What about the fifth one? R2SiCl2. Okay, some correct answers I've got for fifth one also. Let's see. R2SiCl2 first on hydrolysis produces R2SiOH whole twice. And then on polymerization produces which type? Which option now? Tell me. Yes, now all correct answers are pouring in. Yes. And we end up getting so good. Your preparation is going on good. Practice more variety of questions of all types. And let's continue with our discussion. Very good. Answer this. Now we are in metallurgy now. I have landed in metallurgy and this session I'm going to complete it. Incorrect statement. Yes. Impure copper strip is used as anode, not cathode. So the first one is the incorrect statement. Very good again. Yes. Students, actually, I didn't want anyone to miss Ellingam diagram because I can see people slowly joining. Now let's complete metallurgy today. Everyone knows that the ore used to get iron is hematite. And when we take the finely divided ore, since it's an oxide ore, we'll go for gravity separation to concentrate it. Calcination or roasting, we'll go for calcination. Roasting is for sulfide ores. Oxide and carbonate ores, calcination, where you can lose moisture, the organic and inorganic impurities form their volatile oxides and they go off. So you ultimately after calcination obtain Fe2O3. Take it in the blast furnace along with coke and limestone. You know about those different zones, right? Reduction zone, slag formation zone, zone of fusion, zone of combustion. Starts with zone of combustion and then goes to reduction and slag formation zone. Along with the slag which forms the upper layer, pig iron is obtained which contains a around 4% carbon as impurity. Now, we have to see in today's discussion the journey from pig iron to cast iron and finally to the purest form of iron which is known as a wrought iron. So in pig iron, the main impurities are carbon, sulfur, manganese, silicon, phosphorus. Let's see what is this puddling process and how do we get wrought iron. As I was just now mentioning, from the blast furnace, what we get is pig iron, which contains around 4% of carbon and many other impurities, as just now mentioned. Now, you have to melt pig iron along with scrap iron. What is scrap iron? Do you know? I- Some iron objects which sometimes you don't need. Some old iron chair which has like gone rusted and you just sell it to the what kabadi wala. So those scraps pieces, waste pieces of iron. So pig iron plus those scrap iron. All melted together, coke is added, and a hot blast of air is passed. And what we get out of it now is known as cast iron. Because here, when you pass a hot blast of air, a lot of impurities will get oxidized. When you pass a hot blast of air, you will see the impurities getting oxidized. So the percentage of carbon has come down to 3%. Now it has become extremely hard and brittle, but it's still 3%, 4 to 3. What a big deal. Puddling process is what I would like to discuss now. Rollers. This rollers comes here. Overlaps, sorry. So, wrought iron or malleable iron is the purest form of commercial iron. Take cast iron, which still has some 3% carbon as impurities, and add it where? In a furnace which is lined with hematite. What this hematite will do, Fe2O3. So, you'll take this cast iron in a furnace which is lined with hematite. What this hematite will do? This hematite will react with this carbon, the impurity, and oxidize it to CO, gone carbon. Yeah, it's still 0.25 to 1%, depends case to case. Carbon impurity is there. I'm sorry, zero point 0.1, not 0.25 to 1. I'm sorry, slip up. zero point 0.1 to 0.25%, quite less. 0.1 to 0.25% carbon is still there, but most of it will be oxidized by Fe2O3 into Fe and CO. Limestone, which is added here, also limestone is added as a flux. And sulfur, silicon, phosphorus are oxidized and passed into the slag. So when you're oxidizing those cast iron along with those impurities, silicon oxide, sulfur oxide, phosphorus oxide will be formed. So we'll get acidic oxides as the impurities. So in the furnace, when you pass air or oxygen, the furnace lining made with hematite, hematite will convert C into CO. Good thing. The impurities, silicon, sulfur, etc., get oxidized. SiO2, P2O5, SO2, etc., are formed. This will react with CaO and turn into slag and can be removed easily. Slag is a fusible mass. Now, the metal is removed and freed from the slag by passing through rollers. Okay. Slag is produced because the impurities gets oxidized and then we add a basic flux. The carbon in it will be oxidized by hematite into CO. Wrought iron contains 0.1 to 0.25% of carbon as impurity, quite less, manageable, chalega. So this process is known as puddling process to produce wrought iron, which is the purest form of commercial iron. Fine. Anything you can always ask. So here, manufacturing steel from cast iron. So how was cast iron produced? Pig iron plus scrap iron was molded, like taken together, heated so that it melts. Coke added, blast of hot air passed. Here, in bessemerization, what happens is pig iron, which is the most impure form of iron, contains a lot of impurities associated with it. It is oxidized by air. The pig iron is oxidized by air in Bessemer converter so that these impurities form their respective oxides. SiO2 is acidic amino basic. Acid and base will react to form slag and hence they are removed. So ensure you have both acidic no. If you don't have basic impurities also you can add CaO. You just add CaCO3, heat it, it will give you CaO. CO will combine with these acidic impurities. Or if suppose Mn is there and MnO is formed, MnO is a basic flux here acting as a basic flux and all these impurities will be removed in the form of slag. And so this way we will purify iron. Pig iron contains a lot of impurities, students. So we have to purify that iron and then we will add manganese, chromium, carbon will already be there according to me. In cast iron, sufficient carbon is already there. So we should basically add manganese and chromium into it and remelt it. And this form of iron is known as steel. So you should know in steel, you should have Fe, carbon, chromium, manganese. Fine. Try this. Easy, very easy. Of course. So let's understand what is puddling process. Recollect. Students, this is my way out. Like now though I've completed, I'm not I've overcome your stage, but still, whenever I used to study, suppose I've studied something now, not entire thing would be possible. Time is a very big problem. So puddling process. So we'll take cast iron and we will put it in a furnace. We'll oxidize it by supplying air, and the lining of that reverberatory furnace should be containing hematite. Hematite will oxidize C into CO. Hematite will oxidize C into CO. The impurities like silicon or sulfur or phosphorus will be oxidized. And when we add limestone, CaO will be produced on its decomposition. If you heat it, it will decompose. CaO will act as basic flux, and that CaO will react with those acidic impurities, as a result of which slag will be produced, and the impurities can be removed in the form of slag. So, wrought iron, which is the purest form of commercial iron, contains 0.1 to 0.25% of iron in carbon in it. Carbon in it. Yes, that's the way. Ellingham diagram. Most of the things I did yesterday in metallurgy because slowly I want to take up this topic. Students, in Ellingham diagram, what we do is basically we will plot delta G, that gives free energy change, versus absolute temperature. That means temperature in Kelvin scale. We want to plot Gibbs free energy change versus T, temperature in Kelvin scale. Now, students, metal plus its plus oxygen, it's oxide. There's some different metal M dash to differentiate this M dash plus O2 gives M dash O. Which one is more stable oxide, MO or M dash O? First question. Which will go slower as I told. Oxide is more stable, and knowingly I could have given you some question towards the end when it becomes too rigorous and too repetitive and monotonous, but I wanted to ensure most of the people could attend Ellingham diagram in case they don't know what is it exactly. So the answer is the oxide of M dash, I mean M dash O here as given here, is more stable. Reason, its delta G is more negative. more negative is the value of delta G, greater will be the stability of that particular oxide. Now, I'll write two equations and you have to agree which one is correct, which one is not. So greater, so the one which is lower in the curve, or the ones delta G is more negative. So if I extrapolate, this comes around somewhere close to minus 400. This comes somewhere somehow close to minus 250. Greater the negative value of delta G, or more negative is the value of delta G, greater will be the stability of its oxide. So M dash O is more stable than MO, number one. First analysis of Ellingham diagram, number one. Next, there are two things possible. I'm talking about displacement reactions where M plus M dash O gives MO and M dash 1, equation 1. M dash plus MO giving M dash O and M. Which reaction, delta G is already written here, which reaction out of the two is feasible or both are feasible? Equation 1 or 2? Now, since we just now discussed that M dash O is more stable than MO, so that reaction in which more stable is formed from less stable. This is less stable, as we discussed, and this is more stable. So definitely we would like, we are not crazy, right? So definitely we would like more stable thing to be formed from the less stable one. Hence the answer is equation 2, which clearly indicates yes. Everyone following, right? One is not feasible or two is feasible. Same thing. Good. So many answers. Now, if this is the case, then the metal which is lying lower on the Ellingham diagram is more reactive and is a better reducing agent. Means if second equation is more feasible, M dash is acting as a reducing agent, right? Is a better reducing agent than M. And today, I've not forgotten actually. I'll explain why at a temperature below 710 degrees centigrade, CO is a better oxidizing agent, reducing agent, and why above that temperature, carbon or coke is a better oxidizing agent. That is extremely important. They ask in exam. This slide clear? Understood everyone?
Yes, ma'am.
Okay. If not, you will let me know. Okay. It's a whatever we told, basically it's written here. So thermodynamics of the reduction process is explained or understood with the help of Ellingham diagram. It is basically a plot of delta G versus delta S. I'm sorry, delta G versus T. If delta G is plotted versus T, what is the slope of this reaction? What is the y-intercept of this reaction? This is Gibbs Helmholtz equation. Delta G is delta H minus T delta S. So here, when delta G is plotted against T, slope should be delta S or minus delta S. Help me out.
Minus delta x.
Slope is equal to M, which is equal to, because y is mx plus c or c plus mx, right? minus delta S. Good. What about the y-intercept? Followed everyone? Hence, yes, very good, very good. So everyone here knows that at constant temperature and pressure, at constant temperature and pressure, if delta G is negative, the reaction or process is spontaneous. Delta G is positive, means the reaction is non-spontaneous. That also is known. Fine. Gives Helmholtz equation, okay, delta G negative at a given temperature and pressure, it's a spontaneous process. If it's positive, it's a non-spontaneous process. That's also is clear. Fine. Now, if there are more than one such reactions taking place, so many reactions are taking place, right? Two we saw just now. Then which particular oxide will be more stable, or which particular element can act as a better reducing agent, can be understood with the help of Ellingham diagram, which plots delta G versus temperature in Kelvin. Just now discussed, just mention the option. Absolutely. This one I'll explain. Wait, listen to me carefully. This is my work, my task. Students, this is one. This line is one, so that we don't have to write so much, it's written here. This line is one, and wait. Mm, C plus, I'm sorry, this line is 3. This line is 1. This line is 2. I'll justify that. Wait, give me a minute. First, I'll justify, and then if this is wrong or something, I can correct myself. So, this means that out of the 3 lines before this dot, out of the 3 lines, this reaction is most feasible. Everyone listening to me? So, this line is 3. This line is in the Ellingham diagram. It's like this. 2. This line is 1. CO plus half O2, CO2. So, can I say before the dot, talking in more in layman terms, like what we are doing, not before the dot, for equation 1 or for, yeah, whatever, the first equation, the reaction is most spontaneous and the delta G is most negative. Before the dot, one is most feasible. Before the dot, one is most feasible. Understood, right? Fine. So, before the dot means temperature below 710 degrees centigrade. Before the dot. So, before the dot, Fe2O3 combines with CO, because before the dot, this reaction is most feasible, where CO should be on the left, CO2 should be on the right. Giving Fe and CO2. I'm not balanced. That's not very mandatory here right now. We are not learning balancing. So no, many people I get after the class and something, ma'am, you are not balanced this particular. I said you balance on it on your own. I'm here to explain you something. So students, did you get my point? Before the dot or below 710 degrees centigrade, the reaction which is most feasible out of the 3 is CO plus half O2 giving CO2. That's the reason. Below 710 degrees centigrade, the most stable oxide which is formed in the product side should be CO2. And that's the reason I've justified my point. But before above 710 degrees centigrade, the most feasible reaction is 2. Above 710 degrees centigrade, the most feasible reaction, or the ones whose delta G is most negative, is 2, which means carbon should be on the left and carbon monoxide form should be on the right. Above 710, equation 2 is, that's what I told. If I would have gone wrong, no, here I couldn't have justified this. Absolutely correct. So 2 is most stable or most feasible reaction. Above 710, 2 is most feasible reaction. And that most feasible reaction means C should be on the left, CO should be on the right. CO should be formed from C. Done? It's correct. Hence, CO is the reducing agent below 710 degrees centigrade for the reduction of Fe2O3. Above 710 degrees centigrade, it's coke which is most suitable. Basically, in the reduction zone, CO did and should do whatever it should do. But it's in certain cases, no, what happens? Still, you'll see that some Fe2O3 is not converted into Fe. Then, when it goes to the slag formation zone, coke will reduce the remaining left out Fe2O3 into Fe and CO is produced. Any doubts here? Let me know. This is very important. You please memorize and go in the exam what is 1, 2, and 3. Number 1. Number 2, you please also remember below 710 it's CO and above 710 it's C, which is the most suitable reducing agent for the reduction of Fe2O3 into Fe. Clear everyone? Following? Wait. Huh. Ma'am, if CO2 is more stable then why does it become unsuitable after 710? After 710. After 710, it is observed. See, all our experimental observations and whatever they have told us. After 710, what we see is this reaction. The formation of CO is having its delta G. And how do they calculate? They take delta H, delta S at a particular temperature, and then they do this. So if you increase this T and if you keep delta H and delta S constant and change T, delta G value will constantly change. If I keep a delta H and delta S constant, no, and change T, T is changing, delta G will change for all. Say for example, if I like take some 10 people from here, and I think amongst them some things very good they will do. So I check their scores, first test, second test, third test. So amongst them, always the same person will be first and the same person will be second, third, fourth, fifth, sixth. No, they'll mostly be the top rankers. But can become fifth, fifth can become second, sixth can become eighth, seventh can come to the third position. Getting my point now? Like that. That's the reason when I change temperature for all of them, because each will have different delta H and delta S value, right? So this after this temperature, it was found out that the delta G is most negative for this. This reaction is most feasible. So I should ensure that C should be on the left, CO should be on the right. Below that temperature, 1 is the best one. So I should ensure CO should be on the left. Means I should take this as a reactant and this automatically will be formed. I should take this as a reactant and this automatically will be formed. Fine. Please feel free to ask. Certain times I can also learn something from you people. No, if you have a better idea or better explanation, most welcome. Please feel free to ask whatever doubts you are having. Or if you want to discuss anything also, do that. Yes. Students, concentrate on aluminium and magnesium. Can you tell exact temperature? I'm not able to say because I don't remember it. And approximately, if you can talk about this red dot, I'll call this as the transition temperature, no doubt. So around how much? Around 1600 Kelvin will do. So if I don't exactly remember. Chalo below um, red dot. Chalo. If I write here a value, if it's 1600, I'm telling, and if it's 1573, then again you will be angry. So exactly, since I don't remember that value, below the red dot, which is the stronger reducing agent, Al or Mg, which is better reducing agent? Let's see. Okay, answer another question. Which oxide is more stable? So below red dot, MgO is more stable than Al2O3. That you have to agree, it's clearly given here. If that's the case, if MgO is more stable than Al2O3, Al2O3 should react with Mg to form MgO and Al, because I want more stable from the less stable one. Hence, if MgO is more stable, it has to be formed by the reaction of Mg with Al2O3. So Mg is the better reducing agent below the red dot. Language below the red dot. Mg is the better reducing agent below the red dot because MgO is more stable than Al2O3. Above transition temperature and little more decent terms. This is Al2O3. This MgO. Al is the reducing agent because Al2O3 is more stable than MgO. So we'll take Al plus MgO. As I said, balancing, I'm not doing so much time is not there. So since more stable has to be formed from less stable, so it's below, above transition temperature, aluminium is the reducing agent. Below transition temperature, Mg is the reducing agent. MgO is more stable below transition temperature. Al2O3 is more stable than MgO above transition temperature. Followed everyone? It's not that difficult. No, in the moment some people see this, they get confused. I've split it into parts. But I'll tell you first what is Gibbs-Helmholtz equation that I didn't say though. You delta, but no one asked. Delta G is delta H minus T delta S. Then I said that I'll plot delta G versus T. So the slope is minus delta S and my intercept is delta H. And when I plot more than one reactions there, the one which has higher feasibility is the one in which the delta G value is more negative. If the delta G value is more negative, that's the reaction which is most feasible. And on the basis of that, CO is a better reducing agent below 710 degrees centigrade, and C is the suitable reducing agent above 710 degrees centigrade when Fe2O3 is converted into Fe. And here also, I gave some clarity, and I'll give you one question. Students, Ellingham, other things are a lot of it based on memory, liquation and pooling and cupellation and etc. etc. Fine. This part is logic based. You have to let me know if you have any difficulty. Huh. Below point A, Mg is the reducing agent. Above point A, Al is the reducing agent. Below point A, formation of MgO is more spontaneous. Of course, all the above. Very good. Yes. But is it like logically okay with you people, or like something we have learned and we have just correlated so it's okay, or she's telling? Ellingham diagram is important. Could you understand what we discussed? Okay, fine. Yes, I got it. Give me a minute. Yeah, because we completed. And before starting DNA block, I can ask you a few more questions. Give me a little time to like ask you some questions on metallurgy. Yes. Till then, why don't you draw, or like why don't you like little bit recollect about orthosilicate, pyrosilicate? I think so. This would be good enough. I can draw these two also. Meanwhile, I can give you the required question. Okay. So dot O minus O minus O minus O minus. The sixth one. Okay, I've started getting answers also for that. Very good. What's the problem? Which one is not that appropriate? Let me know. Liquefaction is a process where the melting point of the metal is less than that of the impurities. So in the sloping earth, when you heat the impure metal, the Metal will melt first because it has a lower melting point and it will flow down and will be collected. That's correct. Zinc has lower boiling point, so it can boil off as a distillate. Zinc, cadmium, mercury. Okay. Tin, lead, antimony, bismuth. Electrorefining of copper we saw yesterday. Polling is done for which all elements? Not for lead, right? Polling, no, all the options are not correct. Polling is done for, tell me, SN and CU.
Okay.
So this is the incorrect match. Lead you can go for liquefaction if you want to purify it. Yes. Hence D is the incorrect match. Okay. Easy one. No, no. Okay. Okay. One more and then we can slowly go to D and F block elements. I know I've given here one extra. Can you match them? Here A B C D. Here 1 2 3 4 5. Okay. It's already always given like this. Some not always like sometimes. By the way, this is need 2016. I'll not give you options here. I will just write it like this. A. I'll not tell you the answer. A. Which one? B. Which one? C. Which one? D. Which one? Okay. Student, cyanide process for extraction of gold, where gold cyanide's aqueous solution plus oxygen as the oxidizing agent converts gold into the following complex. The following complex will be formed. AU similarly, AU plus CnAO plus Cn minus will be there, water will be there, oxygen will be there, and this complex will be formed. Later on, when we treat it with zinc, ZnCN whole 4, a stable complex will be formed, and Ag, I'm sorry, here Au will be separated. Froth flotation is for sulfide ores, no doubt. Electrolytic reduction is for S block and aluminium. Third, zone refining. It gives you ultra pure gallium, germanium, silicon, hence one matchup. 4231. 4231. That's the reason extra was given to confuse you. Nickel is purified by Mond's process. When nickel is converted into volatile nickel tetracarbonyl, which when strongly heated gives you pure nickel. Very good. So many people answering is a very good indication. Done. If it's done, I'll close this and then open the other slide relating D and F block elements. At max, if you want one more question, we can um, discuss. Yesterday only we discussed. No, everything is seeming very easy to me. So I was thinking which one to ask and which one not. Everything is seeming so easy. Huh. This is easy again. Leaching can be used for which set of metals? For concentration, of course. Very good. Silver gold cyanide process and aluminium halls and Bayers and Serpex. Very good. Which means I'm like kind of satisfied. One more from P block. Good. See, I don't have much time because definitely when I taught something, I would be very eager to ensure that you're in a position to answer standard questions or not. Perfect. What else should I ask? Yes. Geometry of PSiH3 whole thrice CH3 whole thrice N and respectively R. Yes, and after this we should start DNA block. Students, DNA block I'll be teaching, and after that coordination, and then it ends from my end. So if there are, and that this is the reason I asked this question. I know you'll have this difficulty. Those people who have already attended DNA block, I leave it to your wish. It's optional. You can, or you can just go and study. The ones who have not attended, I would request them to definitely attend. That's it. Students, here you have gone wrong in one place. Means not everyone. I have seen one or two things in the chat. Carbon doesn't have vacant orbital to accept lone pair from electron. Carbon doesn't have vacant orbital to accept electron from nitrogen. No back bonding. Nitrogen is sp3 hybridized and it's trigonal pyramidal in shape and tetrahedral in geometry. More specifically, let's talk about shape geometry. Chalega, anything is fine. Now next. Nitrogen says I have a lone pair again. Silicon says yes. 2p here and 3d here. I have a place where I can accept the lone pair. So it's no longer present in a hybrid orbital. Back bonding is seen here. And as a result of this, it is the structure should be not like this. Lone pair is not available on it. It's present on any of the vacant orbitals on any one of the silicon atoms. sp2 and planar, yes. It has a lone pair. But is back bonding possible or not here? What's your answer? Think and tell. Yes, absent. Not possible because 3p, 3p, the orbitals are very large for proper back bonding to occur. So no back bonding. Very good. I'm relieved. Remaining, if you study, and you can ask me doubts anytime, me or sir, anyone. Here, the reason is carbon doesn't have vacant orbital. Yeah, yeah, correct. To accept electron pair. No back bonding. 3p, 3p, Difficulty in overlapping. Too big to overlap. Difficulty in overlapping. Too large to form. Very good. These two I know I have only discussed. This one I had added to the list. Fine. Give me a minute to close this chapter and start D and F block. We started? Yes. As I told, I'm correct, no students? Here, some people have attended D and F as well as coordination. Others are there who may have joined little late, so they have not attended those. Yes. So I leave it to your discretion, your wish, whatever you want, you can do. For me, the remaining two chapters which I have to discuss, nothing else is pending, right? So I'll discuss DF today onwards, and after that, we'll start coordination compounds. And then, as usual, after those two, I'll give you some questions on those two also. I'm more than satisfied. At least in inorganic, you are doing a good job. So let's start our discussion today, right now, here. So there's no doubt about its position in the periodic table. Groups 3 to 12 belong to D block. What's the definition of D block? These elements are known as D block elements because the electrons in them are successively filled from D1 to D10. And D is basically the penultimate orbital years. It's not the valence shell year. It's the shell before last. You know all these things. Students, do you also know the fact that group 12 is not known as a transition element? Yes or no? Group 12, zinc, cadmium, mercury. Because they already have a completely filled D subshell. And the definition of transition element says that the D orbitals should be okay, pseudo transition elements. Fine, fine, fine. And we'll not waste time. So my focus is to tell you all the important things. And if possible, yes, in other cases, the incomplete D orbitals are there either in their native state or in their most stable oxidation state. But here, zinc or Zn2 plus, whichever you take, Cd or Cd2 plus, whichever you take, He and in the most stable oxidation state is not plus 1 but plus 2. In its most stable oxidation state also, it has completely filled d orbitals. So they are categorized as non-transition elements, pseudo-transition elements, or pseudo-transition elements. So in between S and P, in the middle, they are sitting in the middle row, people. Groups 3 to 12 are the ones in which the d orbitals are successively or progressively filled in four periods. Which period? Third period, fourth period, fifth period, sixth period, and seventh period also, right? Fourth period, not third. That's what I wanted to hear. Anyways, I didn't give much time also. Fourth period, fifth period, sixth period, seventh period. So there are four series. 3D series, which you must have remembered each and every element here, right? And which are the two elements which show exception in their electronic configuration in the 3D series? Chromium, copper, everyone knows. So we should discuss something new. In the 4D series, anyone who shows exception, there are many who show exception. There's someone who shows special exception. Okay, anything you know about the 4D series? Ag, molybdenum, palladium, 4D10, 5S0, palladium. I would 100% agree. Palladium is absolutely correct. But when you dig little more in this chapter, you'll observe that nihonium, molybdenum, technetium, ruthenium, rhodium, palladium, silver. All these people are not strictly following whatever rules we have assigned according to the Obos principle. No, they are not following. Nihonium, yes. I'm so sorry. I'm so sorry. Nihonium, no, not nihonium. That was nihonium. Niobium. Niobium. I'm sorry. NH. Nihonium. NB. Neobium. Yes, I corrected myself. 6D series and 7 5D series. Anyone you know who don't follow the rules? Perfect. Neobium. Yes, yes, absolutely no. Corrected. Yes, yes, these two are the culprits. And okay, maximum oxidation state, osmium. This chapter will go very fast. Yes. If I have, and I am not promising or anything, I can't guarantee, depends upon how much of things are left and how many classes are assigned. Towards then again I ask you organic and physical chemistry questions also. Okay. So there are 40 D block elements. First shell 2 electrons, in second, third shell 8 electrons, fourth, fifth 18, next shell 32. Yes. So there are total 40 D block elements. But I hope you know, after lanthanum, it was found out that lanthanum has 14 more friends which will have similar properties as that of lanthanum. But when you have similar properties, how should you? Yeah, lanthanides, no doubt. How should you place them? If someone has similar property, they should be placed in the same vertical column known as group. So there are 14 people who have similarities with lanthanum, and if you have similarities, then you should place them under the same vertical column. Periodic table would be looking very weird, no? Very uneven. For that reason, 14 of those lanthanum's friends starting from cerium to lutetium, they were placed where the anti-penultimate n-2 F subshell is successively filled, and they are known as DNF, but together only we are doing, right? Lanthanides. They are the ones in which 4f orbitals are successively filled. Yes. Connection here. Actinium says you're alone or what? I have 14 such friends whom cannot be placed in the vertical column one below the other, because again the periodic table looks weird. So again, starting from thorium to lawrencium, those friends should be placed below the periodic table, and here the 5f orbital is successively filled. So the capacity of these lanthanides and actinides are 14 each. Just like the maximum capacity of the F subshell is 14 electrons. So these are your actinides. Fine. Electronic configuration. The general one is ns n minus 1 d1 to 10 ns 1 to 2, but you will see so many exceptions here. The right lock, the right key will open the right lock. This is the general electronic configuration where n stands for the valence shell and n minus 1 stands for the anti-penultimate shell. So n minus 1 is the anti-penultimate shell. N stands for the outermost shell, n minus 1 stands for the anti-penultimate shell. The reason for this exceptions in the electronic configuration, which right now you'll be seeing, students, this n minus 1d orbital and ns, they have very small energy difference. Number one. Number two, wherever there are half-filled configurations, you'll know that they are much more stable than other configurations, and that's the reason nitrogen has first ionization energy greater than that of oxygen, right? Even its electron gain enthalpy for nitrogen is very less. Basically, it's positive. It's not willing to gain any more electron and become unstable. So because of the stability of the half-filled configurations and completely filled, no doubt about that, and the energy difference between this n minus d and ns subshell being very less. These are the main reasons why the d block elements show so much of exception in the configurations. Yes, the energy difference is quite less. So easily the electron can jump from here to here, here to here, and half filled and completely filled orbitals are much more stable than the other configurations nearby. Hence, these are the elements which do not follow the rules. Rg. Rg, you know what is that element? I'll not boast that I remember or something out of mainly this F block and last of D block and all. Rowent Janium. You people remembered it? Pakka? True. I recently I had to once. Very good. Very good then. Because they are not like our silver, gold, platinum, or mercury or sodium. And so many. Very good. Impressed. I am very much impressed. I'll tick the culprits. Here the reason is very simple. The stability of the half-filled and fully filled configuration is the reason for this anomalous behavior. Fine. Students, just like that, because later on when we discuss, we will definitely take those things into account. Just like that. In case some people have studied coordination also. Which is the most stable oxidation number for chromium? We'll follow the sequence. But just like that, I felt like asking you. No, no. No to some and yes to some. Only one you have to answer. Most stable configuration of chromium. Chromium, I said. I asked. I mean, okay. I have to discuss this. This is an important thing then. What about copper, which is the most? Copper shows uh, variable oxidation state of +1 as well as +2. For copper, okay, many of them are answering correct. Now, let's discuss. Chromium is more stable in the +3 oxidation state. The reason, let me write its configuration chromium 3D argon 3d5, 4s1. Chromium 3 plus, 3d3. First, this electron will be lost, one gone, two more gone from here. One and two more, total three. Don't look at it as just three. In that sense, you can argue. Ma'am, what are you telling? D5 will be very stable. Just remove one electron. Cr plus one will be more stable. Not plus three. Why are you saying plus three? Why not plus one? Is that coming to your mind or not? Now, when you go to crystal field splitting theory in octahedral field, chromium mostly forms octahedral complexes. Octahedral crystal field splitting takes place as T2G and EG. Very good, very good. So in an octahedral octahedral field. So obvious, I in case you don't know the background of DNF and coordination, I do understand 100%. Okay, and would agree also that if you think CR is plus one and that should be the most stable, you're from if you don't know all these things, it's 100% okay. But let me correct you, it's not plus one and plus three because chromium mostly forms octahedral complexes. In the octahedral field, the d orbital splits into stable E2G and the less stable EG. And D3 means follow Hund's rule 1, 2, 3. The T2G orbital, very good, very good. That's T2G orbital is half filled. Remaining definitely we'll discuss after lunch. But one thing, let's complete this also. So Cr3 is the most stable oxidation state of chromium here. Let's come to Cu. Which one, plus one or plus two? Or you'll find out in the break. That's better. That's better. So your one task I always give, no, sometimes. So Cu plus one or plus two, which is the most stable oxidation state related to your DNA block elements? Yes, now. Which are the ones which are not following rules? We'll hold it here and it's called niobium. See? Technetium, ruthenium, rhodium, palladium, though still very weird. Silver. Fine. Gold and platinum here. Rg. Atomic radii. Let us discuss atomic radii in the next class. Fine. And your task, see you which plus one or plus two. Gave you two options also. Which is more stable and why if possible. Thank you right now. Again, let us meet after the lunch break with more enthusiasm. Yes. So we have only two chapters. We started with P 13, 14, 15, 16, 17, 18. My God. The journey of P over. Metallurgy over. Today DNF. And then coordination. I was literally thinking how will I do so many things, and you made it easy for me. So right now we'll do DF followed by coordination. Thank you everyone. Right now, bye. Okay, I got an answer, but let's discuss it after lunch. Huh? Bye.
Thank you, ma'am. Bye, ma'am.